Yeah.
Nice to meet you. Yeah.
So, I think we'll start. So today we have this guest lecture on experiments on numerical simulations of initiation and growth of cracks under the mixed mode 1+3 loading. Like Professor Krishnaswamy mentioned, to give a brief about his biography, he received his bachelor's degree from Bangalore University in 1973, and his diploma in aeronautical engineering with honors from the Madras Institute of Technology in 1976. He received his MS and PhD in aeronautics from the Caltech in 1977 and 1982. He currently holds the MC Bird and then the Mary Bird Indoor Chair at the Department of Aerospace Engineering and Engineering Mechanics, the University of Texas at Austin. And his research interests are in the general area of mechanics of materials. He is the editor-in-chief of the International Journal of Fracture. He has served on numerous professional organizations, member of the U.S. National Committee on Theoretical and Applied Mechanics, vice chair, chair, past chair, in various positions, and member of the Congress Committee on the International Union of Theoretical and Applied Mechanics between 2010 and 2018, president of the American Academy of Mechanics 2010 to 2012, president of the International Congress on Fracture 2005 to 2009, executive committee of the Applied Mechanics Division of the ASME 2003 to 2008. He is a fellow of the ASME, the Society of Experimental Mechanics, and the American Academy of Mechanics, an honorary fellow of the International Congress on Fracture, and the founding fellow of the Indian Structural Integrated Society. He received the Murray Medal from the Society for Experimental Mechanics in 2004, Tucker Medal for the American Society of Mechanical Engineers in 2015, and Prager Medal from the Society for Engineering Science in 2020, and the Yokoburi Gold Medal from the International Congress on Fracture in 2023. So with this few words of introduction, now I welcome all of you, both in the online and the hybrid mode, to this guest lecture by Professor Chandar.
Thank you. Thank you for the kind introduction. Pleased to be here to talk about this topic. I'm severely jet lagged. I came in at 2:30 this morning, but I think I'm going to be okay making the presentation once I get started. If you're very observant, you might have noticed the title's different from what he read out. The part about cracks under mixed mode 1-3 loading is what I'm going to talk about. I'm going to talk about experiments in numerical simulation, but the phrasing was too long to fit in the slide, so I converted it into emergence of echelon cracks, because this is a phenomenon that happens in many fracture problems. A new pattern appears from an original crack simply by the application of forces in it. And so I thought a more concise title would be what I had on the screen. Kai-Hong Pham and Bisan Lin were graduate students that worked on this project over a number of years. This is culmination of a long program, and I'm giving you a summary of what we learned eventually as to how these cracks form. The motivating problem to me was something that is not from engineering, it's from geosciences. This is a rock formation in upstate New York State, near Cornell University. It's a huge piece of rock that broke apart, and one side of it drifted away, and what you're seeing is what is left on the other side. It was an original crack, a parent crack, this smooth surface, a vertical object, which terminated along this line here. And here's a little box for scale. So these are huge objects. And the ground motion is such that this object, this crack, is under compression and shear. Shearing parallel to the walls of these cracks, parallel meaning movement in this direction, and movement into each other giving compression. As a result of this, from the original crack front, crack starts to grow into the uncracked portion, but it forms a pattern as it goes in there of steps or ridges or echelons. And this is the problem of interest. When and how do these cracks form? Can the traditional techniques of fracture mechanics allow us to calculate or predict that this is what should happen? So you need to go back to classical fracture mechanics, set up a framework for describing such cracks and then asking for the crack criterion. So think that you have a planar crack, what I call the parent crack. That's in the black shaded region, and this line here is the termination of the crack, so it's the crack front. You can establish a coordinate system here. N is normal to the fracture surface of the parent crack, and T is tangent to the crack front at every point. It's a three-dimensional object, so N and T can vary as a function of position along the crack front. There's a third direction in this triad, and we'll call that B, which is normal to both N and T. The question is, if you apply arbitrary loading on that parent crack, what is the extension of the crack into the uncracked region? And that's given here by the shaded green region. It's a three-dimensional tortuous surface that emanates from the cracked front and moves into the uncracked material. And what we need is a criterion that says, if you apply a load of some kind on the parent crack, the shape or the geometry of the new crack will be some deterministic form, right? In terms of the geometry of the parent crack and the loading that's applied on the parent crack. Now, if you create a slice in the NB plane and you observe what goes on here, that new crack is forming along the green line in the NP plane, NB plane. If you know what that angle is in every point along the tangent to the crack front, then you've described the extension of the new crack. So it's sufficient. So that's the first conjecture. It's sufficient to describe what's going on in the NB plane in order to determine what the eventual crack plane or surface would be everywhere. Now, in the NB plane, you can have three symmetries, classical fracture symmetries of mode 1 opening mode, mode 2 in-plane shear, and mode 3 out-of-plane shear. And I'm assuming everybody has had a course in fracture mechanics, that these cracks are governed by the magnitude of the load described in terms of the local values of the stress intensity factors applied on these cracks. So at every point in this, we're going to subject it to a combination of K1, K2, K3 with a superscript infinity to indicate that these are under opening, in-plane shearing, and out-of-plane shearing loading. What is the criterion for growth of these cracks? The mode 1 is the one that's been considered the most. If you look in the fracture literature, probably 95+% of the papers deal with mode 1 fracture because that's the commercially important fracture mode that destroys structures and we need to be aware of. And so I won't talk about that at all because it's very well understood. There are ASTM guidelines, InSIS guidelines on how to design with objects that have mode 1 cracks. I'll say a little bit about mode 2, but the bulk of the talk is going to be on what happens if you have the mode 3 plus a little bit of the mode 1 crack loading on it. So the mode 2 crack in the NB plane looks like this. Here's the parent crack surface, and it's loaded under some loading of K1 and K2 in the far field. The question is, what is the angle at which the crack would grow, and what dictates the load level at which it would grow? This is obtained by using the maximum energy release rate criterion. The crack finds that angle gamma along which the energy released is the largest, and therefore it's easiest to crack along there. I'm assuming it's an isotropic material. Fracture toughness doesn't change with orientation. And that's written here. The maximum of the energy release rate over all angles gamma must equal the fracture energy of the material. But you can get an explicit formula for the maximum energy release rate in terms of the stress intensities experienced by the kinked crack through a calculation that was demonstrated by Aniston and LeBlanc, that the local value of the stress intensity factor, local to the kinked crack, in terms of the global values of the stress intensities, some function of the angle gamma, right? And so you can do this calculation, find the angle gamma at which maximum energy release occurs, and pose the fracture criteria. There are other possible criteria: maximum hoop stress, which is just a stress calculation, find sigma theta theta as a function of angle, whatever angle theta gives you the maximum, that's the angle in which the crack would grow. And the last criterion is principle of local symmetry. In a brittle material, the crack wants to grow in the direction where there is no shear, or where the tensile stress is maximum. So the stress intensity factor in mode 2 on the kinked crack is 0, and the stress intensity factor on the mode 1 crack is equal to the fracture toughness of the material. All of these criteria are very close to each other. Experiments are not able to distinguish between one and the other. And so you could use any one of them and they'll predict what goes on. I thought I'll share an interesting video of this, mode 1+2 fracture. This picture was in a book on tectonofractography. And it's a flask chemists use. And it has cracks on them, if you can see, and they have oscillations in the crack. The crack meanders along. The way this was accomplished was he took this glass jar, heated it up when it was empty, and then poured cold water in it. And as the cold water level was rising up, cracks started somewhere down at the bottom, and they propagate along the sides of the flask. And when they come to a certain point, they oscillate, very nice sinusoidal oscillations, and then straighten out and do various things. We did some experiments on microscope slide glasses. It's about 1 inch wide by about 5 inches long or so. Heat them up to a certain temperature, and then dip them in cold water. So it's the inverse of this. It's heated up, and then you dip it in cold water at the same rate. It dips into the water, forms a meniscus, and then a crack you can see is leading up there, and it's leading up here from this point. The only difference between these two specimens is the temperature change. The left one has 105-degree temperature change, the right one. What happened? It's rebooting.
Are you able to see?
Yeah.
On this side. Oh, yeah.
Yeah. All right. So it dips in, it forms a meniscus at the point of dipping in, and then from the middle of the thickness, you can see a crack rising up. One over here and one over here. The temperature on the left side is 105 degrees, on the right side is 135 degrees. That's the only difference. But you see on the one on the left, the crack is growing straight up from the meniscus. The one on the right is doing a dance. It's meandering left and right. And when you take it out from the water, that's a thermocouple measuring temperature. These videos were taken about 15, 20 years ago. Technology was not very good at that time. You could see a very nice sinusoidal oscillation on the right side, and the left side, the crack was straight. So, and the criterion that I posted in the previous slide any one of these criteria would be able to predict that oscillating crack very easily without any difficulty. So the mode 2 problem, I think, is also a well-solved problem, doesn't need much more attention. Mode 3, on the other hand, is a more interesting, challenging problem. Same picture, I have the parent crack in the NB plane, and I want to know at what angle gamma will it dip. Now the loading is no longer in plane, it's out of plane, mode 3. So the applied load could be K1, K2, K3 super infinity. That means there's a locally perturbed value of K1, K2, K3, which depends on some geometric factor that depends on the angle gamma. Now, the question that is yet to be answered satisfactorily is what's the extension of the principle of local symmetry for 3D problems, that the crack will find the path along which there's maximum tension or minimum shear. People have interpreted this as saying K2 equal to 0. Local mode 2 is 0, but nothing about mode 3, local mode 3. But the mode 3 contributes to energy release calculation. So the same criterion, mode 2 stress intensity is 0. The remaining energy release rate must be equal to the fracture toughness of the material, and that should give you the criterion for the angle gamma. But it turns out that if you do this calculation, it says gamma C should be 0, that the crack must grow straight along the B direction. And that's not satisfactory for two reasons. One, it doesn't make intuitive sense that you shear something and it goes along the shear plane when the material is weak in tension. And two, experimental observations contradict it. The crack never grows along gamma equal to 0. In fact, Sommer and Knaus did experiments some 50 years ago. Knaus did a pure mode 3 experiment. You cut a crack into a long, thin sheet and shear it, just like the picture of the rock formation that I showed in the very beginning. And the crack is under mode 3 completely. And it spawns daughter cracks. Instead of the parent crack moving continuously out, it pops out. It's independent fractures nucleated at some separation, yet to be determined what controls that. So basically, this is what happens. The parent crack is shaded gray. The daughter cracks that spawn out from that are those angled Pac-Man shaped objects. Sommer did an even more interesting experiment. It was a very dominantly mode 1 experiment with an internal crack under pressure in a cylinder. So this is a cylindrical specimen. There's an internal crack with pressure in there. It grows radially out, but then he superposed a torque on it. That gives you the mode 3 along the crack front of uniform mode 3. And he found that when the mode 3 value reached a critical threshold, daughter cracks spawned out, and you had tilted cracks, or the echelons forming along the entire crack face. So people started thinking about this. What is going on in mode 3? A lot of analysis was based on linear stability analysis. You take a straight crack, you perturb it with sinusoidal oscillation or a helicoidal oscillation, and see if the amplitude of the helicoid or the sinusoid would increase or decrease. And they found a criterion that if the local values, the global values of K1 were given, you can calculate the local values of K1, K2, K3, and put this into the energy release criterion and see if the amplitude of the things would grow or decrease. And we found a critical transition point that depended on the Poisson's ratio of the material. A bit suspect, but it's okay. What they concluded was that if the ratio of K3 to K1 was below the red line, the sinusoidal perturbation will be stable, meaning it will be diminished and the crack will grow along the original direction, and unstable when it exceeded that. Now, if we put Sommer's data on there, Sommer found that the instability or the outer plane things started appearing at this level. We did some experiments about 15 years ago and found that the instability set in with a different material, different Poisson's ratio, essentially when K3 was negligibly small. So something is not right about this criterion. So we need a new criterion. So we took a leap of faith. I'll come to the leap of faith in a little bit. So we said, let's do some experiments. And the theory doesn't give you the answer. You need to go to experiments to see what else is missing. So we did a number of experiments. The first one was to see, is there a threshold? Never mind what the value is, but is there a threshold at which these things pop up? So we designed a specimen in which this was a glass specimen, rectangular in shape, under 3-point bending, but with a crack that's slanted at a particular angle, but the crack is not all the way through the penetration. Doesn't penetrate all the way through. It's a 3-dimensionally shaped crack. You can see it penetrates the surface on the back side there. It's circular arc and penetrates again over here. In this side, it's on the opposite face. And this is to get different symmetries of K3 to K1 on the two sides. And we were able to calculate the stress intensity factor very precisely for the 3-dimensional problem using a boundary integral technique. The idea was the following. If you slice it in that plane and show the cracked object, this is the cracked part, that's the cracked front, and this is all uncracked. It's under a combination of mode 1, 2, and 3. But can you see those lines? Just barely. The mode 1 is about that line. This point corresponds to that little box here. So at this location, the mode 1 stress intensity factor is the largest. So you expect that the crack would start there. On the far side, it won't, because the mode 1 stress intensity will be compressive, so it won't start there. Mode 2 stress intensity factor is given by this. In this region of the black box, the mode 2 stress intensity factor is very nearly 0. So we've taken that out of consideration. The mode 3 stress intensity factor is given by this line. And that's the interesting one, because what we've done is make the mode 3 value go from a negative number to a positive number over that length, meaning it crosses 0. So in one test, we can look at what happens at different mode 3 to mode 1 ratio. The two vertical lines here delineate the 2-millimeter region of the box, over which there's a very small variation in K3 over K1, but it spans the range where the threshold behavior was observed by Sommer. So if the Sommer threshold is true, we should see flat crack between these two lines, or basically flat crack here, and then the angle formation beyond that point. But this is what we actually saw. This is a scale bar of 100 microns. This point is the nucleation point of the mode 1 crack, which is right in the middle of that part. The mode 1 crack forms to the right and left of that. You have tilted cracks that are of opposite tilt, because mode 3 stress intensity is of opposite sign. But there's no space over which there's a flat crack that grows at all. What this implies is that there's no threshold. The instant you apply a mode 3 of non-zero value, the crack wants to find the space in which it tilts it and creates a mode 1 crack, and not a flat crack with mode 1 and mode 3 acting simultaneously. This is a glass. This is about the most brittle material you can get. We've repeated this experiment in other materials like polymers that are slightly plastically capable in deformation, but they still do. As long as it's brittle fracture, they still do the same thing. They fragment into multiple facets the minute you do a mode 3 loading on it. So there's no threshold. This is where our results sit. As soon as, and we have some results over here as well. As soon as you apply a small magnitude of mode 3, the crack starts to flip. So we need a new criterion. So here's the leap of faith. We made a different extension of the principle of local symmetry. Instead of insisting that only the mode 2 stress intensity on the tilted crack is 0, you say crack is not capable of shearing at all. So on the new crack surface, you should have both the mode 1 and the mode 2 and the mode 3 stress intensity factors equal to 0, and you only have a mode 1 stress intensity factor. That must reach the fracture energy toughness of the material. This is very easy to impose. The angle at which the crack would tilt based on this is calculated by this simple formula for plane strain. That means the crack should do that. The parent crack is in gray. The daughter crack will be the shaded orange or orange color. But this is a criterion that's not possible to be imposed locally everywhere. It doesn't have translational invariance. If I move to the right, it'll violate it. So basically what it's saying is if I move to the left of this point, the crack should go up. If I move to the right of that point, the crack should go down, if you have a perspective from the B vector. But if I now move a little bit to the right or left, I can't enforce the same thing unless the crack fragments itself, which means it can fragment it further. And there's no clear criterion on what sets the spacing for this fragmentation to occur. There's a lot of suggestions in the literature that this should be the criterion, and here are some references. So we went back to the experiment to see, can we find what sets the scale of this fragmentation and figure out how these daughter cracks link up eventually to fracture the whole specimen. First, about how the daughter cracks could link up. If you look from the negative B direction at a slice in the NT plane, you'll see these cracks. They're separated from each other, but the ligament between them is not broken. So you just have these cracks popping up that are disconnected from each other and connected only at the back of the parent crack, and there's no continuous path to a fracture surface. Eventually what happens is when these so-called A type of cracks slanting to this side start moving, this ligament between them, depending on how wide they are, they create tension, local tension, and they may do a handshake like this. So this crack curves and comes and meets this one. This crack curves and comes and meets this one. If they're close enough together, that's how they meet up. In some cases, they just break as a brittle crack perpendicular to the parent, to the daughter cracks. For us, all we need to know is that when these parent cracks spawn daughter cracks, they're not connected, and there's some energy that is stored in this region, and that needs to be accounted for if you were trying to look for criterion for crack growth, where only partial crack growth is observed. Here are some traces from a sandstone. Parent crack is somewhere behind the screen. It's coming into the plane perpendicular to the screen. They're all slanted, and eventually they do the handshake to link up with each other. And this is the mechanism by which these echelon cracks are able to form, but there's no criterion yet about the spacing between them. So we redesigned the specimen to have stable crack growth over multiple distances in order to be able to see how these cracks interact with each other. So we took the same specimen, inverted the 3-point bend configuration. Now these cracks are under predominant compression and shear. So the compression will prevent the cracks from running away. The shear will make them grow. And so we could have cracks that pop and stop at some point, so we could look at the geometry of that. And I'm only going to show you pictures of what the eventual outcome is. Parent crack is in the background. This is the width of the parent crack. These were cut with a saw, so they have a certain dimension to them. It's on the order of 300 microns or so. They pop these daughter cracks. These are the daughter cracks. Their spacing is about the order of the width of this the groove. So this is the only length scale that's in the problem other than intrinsic material length scales, which are much smaller dimension. So this makes sense that it dictates the spacing. I don't know if you can see this, but these are at a smaller scale. Each one of these is a groove. It's nominally a circular cut, but cut is rough and there are scratches on the cut. They are on the span of 20 to 30 microns or so. They create daughter cracks. So if I zoom into here, there are daughter cracks that are a 20 micron spacing between each other. If I zoom into that, there are undulations on the surface that are on the order of tens of microns, and the cracks are on the order of tens of microns spaced from each other. So it's whatever the length scale of the crack is, crack front is, that dictates the spacing because it's an elastic unloading over some length when the first crack pops. So there's no intrinsic length scale. The scale is governed by the scale of whatever the defect is that triggers these daughter cracks. The next thing that happens is that the daughter cracks grow, but they shield one another from growing, and they lead to what is called coarsening. Goldstein did some experiments in the 2000s, I think, where he took a specimen, which is where we got our designs for the threshold determination. There are cracks on two sides, asymmetric, either tilted or straight, under 3-point bending. So they have this mode 1+3 loading, and they spawn daughter cracks. And here's this cartoon of what the daughter cracks look like. The background parent crack is along that line. The daughter cracks are tilted, and there's a spacing about these. He did these experiments in Gruyere cheese so that it's easier to slice them and see what the daughter crack geometry looks like. So at state A, when the cracks had just started from the parent crack, there was a spacing of those cracks that you can see here. When you allow them to grow by a factor of 10, I think, in length, you see in the same thing, this number of daughter cracks is smaller and the distance is greater. So these cracks that started, they don't make it all the way through as you progress. They shield some of them and only a few of them grow. You make them grow further out from the parent crack, even fewer of them survive, and they become bigger. So there's a coarsening and the corresponding increase in the spacing between the daughter cracks. And we found in our experiments the same thing in a different material. This is now a brittle polyester. Those are the daughter cracks. Parent crack is over here. They're tilted at an angle of 45 degrees for the mode 3 loading. And you can see many families of daughter cracks. So that's the third family, that's the second family, there's the first family that's even smaller. So there's a coarsening effect of these cracks as they grow. It's easy to understand the coarsening with a very simple simulation. Suppose you think there's a system of daughter cracks, periodically spaced, subjected to a mode 1+3 loading in the far field. They create a stress intensity along the curved crack front that allows them to grow. That stress intensity factor, mode 1, is given by these lines. Ignore these two there from the endpoints, which have edge effects that we didn't take care of. If you suddenly allow one of these cracks to expand and redo the calculation of the stress intensity factors are for these cracks, so all of the cracks experience nearly the same stress intensity when they're uniform. If one takes a burst and moves forward, that stress intensity is shown by the red line, it increases. The two nearest neighbors decrease their stress intensity factors because they're shielded. The next nearest neighbor, this one and that one, they don't see any effect of that. They don't get shielded. So there's a clear period doubling kind of instability here. If by any accident one of the crack pops, it will shield the nearest neighbors. The next nearest neighbor can grow. Take that to its conclusion, it'll always period double, and every second crack will stop, and that's what's going on here. Fairly easy to understand. Finally, how do they link up and grow? So for this, we have to create another experiment. This was done on a hydrogel, gelatin-based, the dessert that you make. So we made specimens out of gelatin and put them in mixed mode loading by pulling it in uniaxial tension, but put a sharp angled crack, part through crack at an angle, and observe what happens to that. This material is fairly linear in its elastic behavior up to very high stretch levels, but it's failing at fairly low stretch levels over most of its domain. So here is a video. I hope it works. This is a crack that was scribed into it and then applied mode 1+3. It created daughter cracks, and we've already had that daughter crack system established. And then we continue to load it to see what further progression of these cracks, how do they basically link up and join. So the crack is at a slant to the geometry of the loading, but we're looking at it at a projection. So you could see the daughter cracks starting to grow. And if you pay attention to some of them, they'll fall off. The other ones keep going. We play it again. So somewhere here, you'll be able to see the this crack will fall off. It slows down, and there are others that slow down too. But these are unconnected cracks. They're all at slanted angle, and they keep going. Some of them drop off, but the other ones keep going unconnected. And eventually, something connects them up from the back. And you're not able to see that here, so I have to show you a cartoon of what I think is going on here. So that's the parent crack. It spawns daughter cracks. The daughter cracks grow. They shield, and some of them grow more than the others. But now what happens is you're still subjecting them to this load, but the parent cracks will experience a larger mode 1 loading because otherwise there's no further deformation possible. The parent cracks lock them in and they would stop it. So they would advance and the entire system will keep moving to a steady state. And this is how the pattern survives the coarsening and eventually. Yeah, right.
It has a jet lag, or you?
It has a lag. I don't know if it's a jet lag. So we think that it's trying to establish a steady state by this coarsening process and cutting off from the back. And then you could see that this progression could sever a large surface into 2 pieces. So that's what's going on here. Now you can see there's a spacing of the daughter cracks, and they're all tilted. You can't see that from this picture, but each one is a tilted crack at an angle. And as they grow forward from the main parent crack, some of them get dropped off, and there's a coarsening, and you can see that at this point, one of the cracks, these 2 merge and become 1 crack. These 3 have merged and become 1 crack, and so on. So the shielding is non-uniform because the material is non-homogeneous and there are local defects. So that's what we think is going on. So the question is, can you now simulate this thing? And we're going to do phase field methods to see how we can simulate this. I'm not going to spend too much time on this phase field method, just give an outline of it. So the idea behind the phase field method is to write the Lagrangian for the system, consisting of kinetic and potential energies, and include in it the fracture energy to reinforce Griffith. The idea is that this is over the set of points that form the crack. And that is what makes it difficult to handle. You cannot do this for arbitrarily unspecified crack path. The Euler-Lagrange equations, I don't even know what they would look like to write. But the idea behind the phase field approximation is threefold. First, the surface integral here is approximated by a volume integral. So instead of the integral of the fracture energy over the fracture surface, you do the integral of the fracture energy over a spread out smeared volume, where the volume is dictated by some intrinsic scale of length L naught to be decided, and to introduce a parameter C, which will degrade this material from intact to a damaged material over some magnitude of the loading history, depending on what kind of formulation you do for the fracture energy penalty. This brings in intrinsically length scale dependence, so they've introduced a gradient penalty term to penalize sharp gradients. And finally, to model the loss of material stiffness, you degrade the strain energy in the material based on some assumption on how the damage progresses as well. Now, there are proofs that this will converge to Griffith fracture if the length scale L naught tends to 0, and there are fix-ups for fixing the fracture energy when L naught is not 0. I won't go through all of that, but the basic idea is you've replaced that surface integral by this volume integral term, and now you can write the Euler-Lagrange equations for this easily. And this is the divergence of the stress equal to the inertial term, where we have defined this thing as a new stress, damage-induced stress. CE depends not just on the strain, but also on the damage parameter C. So you get two equations, one for equilibrium of the mechanical forces and the other one for the evolution of the phase field parameter. And I'm going to not go through this thing partially because I'm jet lagged, but the details are a little bit tricky. But basic idea is you take this strain energy to be the undamaged strain energy multiplied by some function of the damage parameter C, and that gives you details of the damaged elastic property as well as the evolution of the damage function itself. There are two ways in which you can damage it. The original formulation of the phase field damaged all elasticity, which led to some artifacts, like you could heal the crack if you unloaded it, or you could crack it when it was in compression and things like that, which was fixed by adding some other features to the model that the damaged elasticity will be damaged only based on the positive parts of the strain energy. I put positive in air quotes because this is energy has no color, but this one does. But and you can do the one-dimensional problem fairly easily. I'm skipping details again. Basically what happens is, depending on what your damage function is, the local behavior of the stress strain with the phase field would be linear up to some point, start damaging at some point, and then peak stress at some level, and then damage continues further, and the material is separated at this point. So you've converted the problem of fracture mechanics into one of elasticity or elastic calculation with this model. But crucial to it is that there's an intrinsic length scale that's been brought into it, and this length scale must be extremely small in order to capture the fracture process faithfully. All right, so it's very unsatisfactory description of the phase field method, but we said let's implement this and see what it does for the problem of mode 1+3 fracture. So we created a very fine discretization of the crack tip regions to be able to see how a mode 1+3 loaded crack will grow. So we simulated only a small domain near the crack tip, applied K-field boundary conditions, meaning displacements based on K1, K3 field was applied at this location. And that's at about 10,000 length scales L naught away from the crack tip, to give you an idea of how long we had to go. And if you now run this thing with modes 1, 2, and 3, you get the following description. If you do a mode 1 loading on it, the phase field method predicts that the crack should grow straight, which makes sense. If you apply a mode 2 loading on it, it kinks and the crack starts to grow at an angle of 70 degrees or so, again consistently with continuum predictions. So the phase field method seems to be adequate for these things. If you do mixed mode, the unresolved issue between which ones of the techniques is good still remains unresolved because this is within the same error bands. But if you do a pure mode 3 loading, crack grows straight because that's the only path that it has along which it can minimize the energy. So it goes straight. Well, we know that that's not true. So what do? We decided to implement the idea that defects are the key. So we introduced defects into our mesh. So how do we introduce defects? You pick a cylindrical volume along the crack front and identify randomly about, I think it was 0.6% of the mesh points or elements, and provide them with damage, meaning that they're completely damaged, C equal to 1. And the rest of the things are intact. So this is now an initial defect field that has been prescribed over this volume, and we let them be subjected to the mode 3 loading. Remember, if that defect system was not there, the crack would grow straight from the parent crack. Now, I don't show you the parent crack. It extends behind on that direction. This is the thickness direction of the specimen. And these defect elements are centered along the crack line. So pure mode 3. And the cracks will become visible when new elements get damaged, not the old elements. So you could see the role of defects. They deflect the cracks from their original path along the line of symmetry. And the daughter cracks or the echelon cracks appear automatically from just that small volume fraction of defected elements. Now, the overall size of our box was not large enough to let this thing go further. It's already reaching the upper limits of the box of our simulation at this stage. And this had 1 million elements or something like that. So that L not being very small prevented us from simulating very large domains, but you could see the sense that the cracks are slanted at 45 degrees for a pure mode 3, and they do what we expect them to do. They appear autonomously once the defects have been produced in there. We didn't need, so ideally I would have defects everywhere in the entire volume, but you can already see that those defects are not going to do anything because defects that are left behind are unloaded and they don't play a further role in the evolution of the crack. Now, let's see if it works. The geometry of those daughter cracks is not going to work. Okay, I was going to show you a 3D view of what that looks like, what this pattern would look like, but we'll see if it we'll come back to the end. So that was under pure mode 3. What happens at the point where the linear stability analysis indicates a transition, right? So we wanted to go well below that and see if these cracks are stable, right? So this is at a K3 to K1 ratio of 0.3. It's below the line where the transition to unstable perturbation analysis results. Same idea, many defects in the field, and then they start perturbing the crack. And when they get out of that, they've already formed a pattern of slanted cracks. The slant angle now is smaller. You can see the angles are smaller than, but there is clear you can see they've established their slant depending on the ratio of K3 to K1. Again, they've run into the end of the simulation domain. So now let's do multiple cracks and see how they interact with each other. So the parent crack is behind. You can see the intersection of the daughter crack with the parent crack. And we put in a periodic array of daughter cracks to see how they would evolve and how they would link up with each other. Now we don't have any more defects in here because the parent cracks are already, the daughter cracks have already been spawned. We don't need defects. So this is at a particular tilt angle corresponding to whatever the ratio of K3 to K1 needs to be for that. So the parent cracks start linking up, they grow. The daughter cracks grow and shield each other. Here is the coarsening. This one and this one grew, the ones between them stopped. And so we've been able to reproduce fairly every feature of the experiment that we were able to see with the phase field method. The only thing is you need defects to start triggering this thing. We don't have enough computational capability to do this on a scale that is structural unless the phase field method gets refined enough to be able to coarsen that length scale L0. All right, with that, let me stop. What we've done is looked at the problem of interaction of mode 3 with mode 1 that spawns daughter cracks or fragmentation of the original crack front, and dealt with some issues related to nucleation and growth of these things. We've shown that phase field methods can reproduce some of the features, but there's an opportunity for doing rigorous simulations at a larger length scale, reaching larger length scales to be able to do structural problems. All right, with that, let me stop. Appreciate your patience, listening to me jet lagged. I'll be open for questions. Thank you.
Thank you. I'm sure there are questions. Please feel free.
So yeah, excellent talk as well. So regarding those defects that you put into the phase, so those are just completely random volumetric in the volume.
So what we did was we controlled the volume percent of elements that would be defective. We did an exclusion zone. Once it was random choice, right? So once you picked a certain void element damaged, certain radius around that was excluded from the next damage, so you don't have clustering. And then we gave them completely damaged value of C equal to 1. You could have had a distribution of damage as well. So we didn't explore all of that. It was just to see whether the distribution or whether the presence of defects would cause the daughter crack to form.
And the length scale of those, like those defects, like no.
Right. So the L0 value is set at a particular number, right? So our element resolution was to resolve 4 L0 at least. Right. So that sets the mesh cell length. Right.
And the defect size was 1.
Defect size is 1 pixel. One element.
So you were trying to predict the rock.
Yeah.
Yes, through combination of mode 1.
Right.
You are able to predict that. Is there any express, we can do those things and then?
Well, we did some experiment not on rocks, but on glass and things like that. But the idea is they're all brittle materials and they should behave the same way. So we did it on model materials, glass and polymers. But you should be able to do them on rocks or clay or something. Clay is a bit tricky because it'll bring plasticity into the picture. But rocks would be, yeah, we should be able to do them.
Can these studies be useful for any of the manufacturing process of making some complex structures?
I'm not sure, but there is one thing that comes out almost immediately. The presence of a mode 3 increases the load that's necessary to crack it. So the fracture, the apparent fracture toughness will go up if you have a mode 3 superposed on it, because the cracks are now no longer favorably oriented along mode 1, they're tilted. So if you had a part that is subjected to predominantly cyclic mode 1 loading, you superpose a little bit of mode 3, it should decrease your crack counterintuitively if it is elastic process, right? So there may be a strange technological application. Yeah.
I was curious about the plot that you showed that you use linear stability analysis. You need a certain amount of K3.
Right. Right.
But experimentally, even if you have very low K3, it still happens.
Right.
But the skew character is a function of K3, right? So that means
Yeah.
if your K3 is very small, the kinking should also be very small.
Right. It is. Yeah,
So
but it's
it means
visible.
like if your K3 is really low,
Yeah.
it should just go like almost like
Well, okay. Now let's see if this will work, or I can get out. So this is what I was trying to show. So this is for pure mode 3. Oops. That's at 45 degrees. Now, if you make K3 below the threshold, so here you can see the angles are much smaller, but they do fragment and it's visible. And this is well below the place where the linear stability analysis says it's stable, right? So the stability analysis is ignoring something. I don't know what it ignores.
one question from Ravi.
Yeah.
Speak up. Yeah.
Oh, sorry, I put that in the chat box. Ravi, thank you. Very interesting. I missed the first part, so I don't know if this is relevant, but there seem to be similarities with ordinary cleavage fracture where a cleavage plane in one boundary at a grain boundary has to
Yeah,
branch.
very good observation. I should have pointed that out. There are some very elegant experiments by Ali Argon, where he looks at cleavage crack in one grain meeting another grain where the cleavage plane is misoriented. And as they pass through, they create the same system of echelon cracks in the second grain. And it's exactly the same mode 1, mode 3 interaction, because if it's mode 1 in the first grain, along the cleavage planes of the second grain, it's a combination of mode 1 and 3.
So I was going to ask: is there a length scale that dictates the number of daughter cracks that would form?
Yeah, I think I mentioned that it depends on the size of the parent crack, some size measured of the parent crack. In our experiments, they were machined grooves, so that set the scale for the daughter crack spacing. In the bicrystal experiment, I think it's something about the number of planes that are involved in the cleavage process, I would assume.
Okay. Okay, thank you.
What's the choice of your choice of the experiments you did with gelatin?
Right.
Why did you choose gelatin? Why not something?
Gelatin has a very slow, stable cracking process. And I could also, it's very easy to see through, very easy to manufacture. And so we picked on gelatin. Also, we were working on gelatin for other reasons during that time, so it came in handy. But our choice of materials is that they should be brittle. They shouldn't have inelastic deformation. So that the three materials that I showed, glass, H100, Homelite 100, the thermosetting polyester, and gelatin, will have very small process zones, and it's basically elastic brittle.
Also, it can be isotropic, right?
Yeah, right. Although there's the bicrystal experiment of argon, they were not isotropic materials, they were two single crystal specimens, so they're not necessarily isotropic, right? Each grain has a certain crystallographic orientation. They have to be brittle, elastic. I think those are the two.
And from what I understood, that your artificial effects that you introduced were more like programmed
Yeah,
species rather than random distributions that you really wanted to.
well, they are random. So I take my coordinates of each element, center of the coordinate of each element, and I have a box.
Mhm.
From that, I'm going to use a random number generator to pick one. And then I might use my exclusion criterion to remove all the other elements that are in the exclusion volume out of the box. Now I go and do a random pick of the next element. It's somewhere. That's
You did that over a controlled time.
over a controlled region because I didn't want to have damage everywhere. Yeah. But I don't think it would influence, the defects far away are not going to influence the nucleation of the daughter crack in any meaningful way.
This is a slightly different perspective. Suppose you did this from a fractal dimension. Would that be able to help us to say that, okay, this is a fractal dimension for this mixed mode tracking, and then if it was kind of pure mode 1 or mode 3, what would be?
I haven't thought about that. I don't know.
Because the moment you showed me that, the rock pattern,
Mhm.
what struck me was, people try to solve this problem through this.
But I see a more regular pattern in there, right? Yeah, I see a more regular pattern there. At every position at some distance away from the parent crack, I can identify a feature. I don't see that there's a fractal dimension to it, but there's this period doubling dimension to it is more evident than anything else. That as I go farther away from here, there are fewer cracks that are longer. And that you can explain by the shielding process. You don't need the idea of fractality for it.
What you say is in sense, because there they would look at self-affinity and
Right.
such in
Right.
So, but still, if you do the fractal dimension for this, maybe, it will show what is the effect of crack shielding on.
Perhaps. Yeah.
Yeah, study.
Similar to this problem, there is also like excavation and mining sites.
Yeah.
Limestone, granite.
Mhm.
So I can see similarity.
Yeah.
Larger scale.
So iceberg cleaving, and when it cleaves and falls into the remaining part of the iceberg, will have this kind of a feature in it as well.
Even the mining sites are having
Yeah.
actually fractured.
So you can walk around hills around here, and you can see this kind of feature in many places. Any rock formation, rocks that fail are typically under mode 1+3, and they'll create this pattern at some scale.
And it's effect of pore pressure because the fluid saturated.
Um,
Will it affect the mode 3?
Perhaps it'll affect the fracture properties, definitely, right? Pore pressure. it might affect the fracture growth as well.
So mode 1 is going to be very stable. If there is more trade and catastrophic damage, like propagation rate will be higher. I'm not sure about that. So will the pore pressure or fluid saturated medium?
So pore pressure effects have a time dimension to them, right? So it depends on whether the cracks are formed instantaneously by overload or whether they form slowly through a poroelastic process. It has to be a slow crack for pore pressure to have a significant effect on it.
Yeah.
As this is over around this loss and price, bringing studies to whole state of cancer. Maybe we can estimate of this, these are our time different roles. Over a time the roles.
Yeah.
But when we are doing experience on these things, first we research. So for these cases, we considering that they were looking at certain.
So the experiments that I did were all over monotonic loading at constant strain rate. Small, but the materials were not strain rate dependent. Fracture was not fast to have inertial effects, so time was not a factor. But in this crack, for example, time might have been a factor. It's in a lake bed, right? So there's water all over. So there could be the effects of water freezing, thawing cycles, could be effect of diffusion, things like that would have happened over a time scale. But that's not the important thing. The important thing here is the formation of the daughter cracks. They happen no matter whether it's a time-dependent process or not.
Geo systems will also have liquefaction.
That's part of the poroelastic thing, right? Yeah. Or you mean frequency dependence of the material?
That is one thing, and also the fact that solid becomes viscous at some pressures.
Yeah, that's a different story. Yeah. This applies when the material is brittle and probably in the elastic regime. Yeah.
Good.
Okay, thank you.
There are no more questions. Once again, and I request Professor Moni to handle. Somebody has a good camera can take a picture of this. So this has a materials testing system.
Make a more 3 crack in here.
I'm sorry? Want to make more specimens out of this? Sorry? Oh, we can. Most. So, thank you all for attending this, and feel free to take those cookies and snacks.